Hey everyone, thanks for tuning in. My name is Tanner Slagle. I'm a civil servant at NASA Langley in the Formal Methods group. I'm going to talk to you all today about a formal verification of semi-algebraic sets and real analytic functions that me and a couple colleagues did in PVS, which is the interactive theorem prover of choice uh, in this office, at least. So let's talk about motivation for this formal verification. In the formal methods group here, we want to be able to reason about hybrid systems. So hybrid systems are dynamical systems that have both discrete and continuous variables in time. So a hybrid system often has a safety critical component. Perhaps it is a human life or some life, or perhaps it's a lot of money on the line. So you really want to be able to formally verify safety properties of this hybrid system. One way to do that is with differential dynamic logic. It is a logical framework that you can reason about hybrid systems. So the overall goal here is to implement DDL in PVS. The issue is that to implement DDL in PVS, it requires a lot of theory of ordinary differential equations, as well as the focus of this talk today, which is multivariate polynomials, semi-algebraic sets, and real analytic functions. A little example in the diagram to the left here. Imagine this as an aircraft, and the aircraft path is a solution to a differential equation. We're going to assume that that's real analytic. And then it is navigating through a geofence, which is the blue line. So a basic property we might want to prove here is that when the aircraft leaves the geofence, it will leave for a complete interval of time. So you can see at the bottom of this blue semi-algebraic set, the path of the aircraft totally leaves the semi-algebraic set for a full interval of time. This is something that I think we would believe about an aircraft, but proving it in terms of real analytic functions and semi-algebraic sets actually takes a little bit of work, but being able to prove that sort of validates using these sorts of mathematical objects as a model for aircrafts and geofences, etc. So here's the way the outline of the rest of the talk is. This is the short version of the talk. I'm going to quickly talk about the formalization we did of semi-algebraic sets to real analytic functions, and I'm going to spend a little bit more time talking about the real analytic function behaves on the boundary of a semi-algebraic set, like I described in the last slide. So when we formalized multivariate polynomials in PVS, the way we did this was we started with a monomial, and we defined it as a record data type. And then a multivariate polynomial would be a list of these monomials. So you might imagine that if you have a list of monomials, there are many examples of syntactically different multivariate polynomials that are actually the same in terms of evaluation. So one big hurdle we had to deal with was developing something called standard form. You'll see an MV standard form here, MV standard form. And we had to show that the standard form of a multivariate polynomial was unique. And that's what this PVS theorem is showing right here. It's saying that if two polynomials have the same standard form, that means that they evaluate to the same value for every single choice of inputs. All right, so once we have multivariate polynomials in PVS, we can go on and define semi-algebraic sets. An atomic polynomial formula is a record type in PVS, and it has a polynomial and an inequality. The way that a vector satisfies an atomic polynomial formula is you evaluate the polynomial at that vector and use the inequality to compare it to 0. If you get true, then that vector satisfies the atomic polynomial formula. So once you have atomic polynomial formulas, we can make a quantifier-free polynomial formula. We chose to define a quantifier-free polynomial formula in disjunctive normal form in PVS. What this means is that it is a disjunction of conjunctions of atomic polynomial formulas. So a conjunction of atomic polynomial formulas is called a meeting, it's a list, and a disjunction of those conjunctions is a joining, and it is a list of meetings. Once you have a quantifier-free polynomial formula, you can define a semi-algebraic set as nothing more than the set of vectors that satisfy the quantifier-free polynomial formula. Okay, so you've probably heard of analytic functions in the complex analysis world. The real analytic definition is very similar, but it is equivalent to a lot less powerful things. So a function, a real valued function, is real analytic at a point, means that that function in some neighborhood around the point equals some power series. In PVS, we showed the sum of two analytic functions is analytic, a constant multiple of an analytic function is analytic, the product is analytic, and a non-negative power of an analytic function is analytic. And all this was enough for us to really get to the meat and potatoes of what we were trying to prove. This is one of two of the main theorems, and this one I call the clean exit theorem. And it is categorizing the exact way a semi-algebraic set or a real analytic function might leave a semi-algebraic set. Basically, one of these three cases happen. The first case is that the function never leaves. It stays in the semi-algebraic set for all moments of time after you start paying attention. The second case is that there is a point where the function is outside of the semi-algebraic set, and the very first point that it exits the semi-algebraic set, it exits just for that point, and then is entirely inside the semi-algebraic set for some amount of time completely. This is basically a function coming up to the boundary of a semi-algebraic set and bouncing back in. The third case is truly a clean exit. The function goes to the boundary of a semi-algebraic set, and then it leaves for an entire amount of time. So you see that f of x star plus t is totally on the outside of the semi-algebraic set for an interval of time. If we look at this graphically, this graphic is showing case 3. We have this real analytic function, and it leaves the semi-algebraic set for an entire amount of time. The second case would look a little different. The real analytic function would come to the boundary of the SA set, which is not in the SA set. It can be, but in this example it is not. And it would bounce back inside the semi-algebraic set. So it would just exit the semi-algebraic set for a particular instance. So this is a pretty basic property. If you take time to think about it, this is a basic property. And you might wonder if real analytic is a bit of a too strong of an assumption. So it's worth noting when you relax the assumption of real analytic to smooth, which means infinitely differentiable, you do not have this clean exit property. This is what it looks like in PVS, but I'm going to describe it with this picture. You have a semi-algebraic set defined as this bottom half of the plane, and this Sm function is smooth, but not real analytic at 0. So this Sm function is in the semi-algebraic set all the way to 0. But then for any neighborhood of time you take after 0, any positive amount of time after 0, there are infinitely many points that are inside the semi-algebraic set and outside the semi-algebraic set. In particular, if you look at these peaks of the function, every one of these high peaks is outside of the semi-algebraic set, and every single one of these low peaks is in the semi-algebraic set. Therefore, Sm does not leave the semi-algebraic set fully for any complete amount of time, and it also doesn't satisfy either of the other two cases. So smooth is not quite strong enough of an assumption, but real analytic is. Well, I hope I did this in 10 minutes. Let me wrap it up a little. I've talked about a formalization we carried out in PVS. I went through it very quickly. If you want to look at the details, check out the longer video on YouTube. Some future work we could do, really I'll skip to the most important one. We need to develop the theory of differential equations in PVS more. In particular, we have the way a real analytic function behaves with a semi-algebraic set, but we need to know when is the solution of an ODE real analytic, and that theory exists in the world. It's just a little piece of the puzzle that we need to implement into PVS. I want to thank the organizers of this conference. You all have done an awesome job. I want to thank you all for listening. And I'm sure wherever I am right now, I'm ready to take some questions and hear your thoughts. So thank you very much for listening, everyone.